I think we're going to go ahead and get started. Morning, everybody. Nice to see all of you. The usual for people who weren't here times before, my name is Anthony, and this is a lecture series from the Enrico Fermi Institute, the Arthur Compton lecture series, and this is the fourth one of a series of 8 on understanding the building blocks of nature with particle collisions and AI. And I kind of liked last time where I started off with maybe something fun, not necessarily related to this. And so the fun thing that I wanted to highlight was that there's new dark matter results coming out of a very interesting experiment called the LZ experiment, where it looks like this. They have a giant vat of liquid, or of a liquid material that has a high cross-section for particles to hit it. They basically wait a lot of time. Particles come in, hit it, and then leave signals up here. And the probability to get a particle hitting it is very rare. And so they use this giant vat of liquid to actually set limits on different dark matter scenarios. And so they just put out a paper today, and then they also put out, there's a YouTube video that explains the experiment, and they put out ideas for next generation experiments where they want to push the limits even further down in some arbitrary units. And one of the reasons I wanted to highlight this was actually the graduate student that taught me a lot when I was a starting graduate student switched to this experiment, and this is her result, and it's really great to see for me. So I would really encourage you to go click the link, watch the YouTube video. It's a really incredible experiment. So today the plan is to go over some particle identification. So this is going to be the first lecture where we talk about an AI tool. We're going to talk about identifying particles and reconstructing events, and we'll go over more of what this means. And this is building on what we did previous times, where we gave an intro to the lecture series, talking about particle collisions generically. We talked about big physics questions ranging from the nature of dark matter to the nature of the Higgs boson. And then last time we shifted our brain from these big questions to the experiment and to AI. And so this time we're going to take the next step and actually walk through an example of something we do every day on the ground. So we're going to start off just like before, where we do a refresher generally of what we talked about last time, and then we're going to go over an example where, for this example, we're going to talk about top quarks and B quarks primarily. So to say it one more time, the coming lectures are going to be about motivating, building, and utilizing AI-driven tools. And so this is the kind of pyramid that we made last time, where at the bottom of these AI systems, we have narrow AI, where we're targeting specific tasks. And then as you go one level up, you get generative AI, or you get generalized AI, where you can do all sorts of human-level problems, and then super intelligent AI, where you can do really next-level types of decision-making. And so this is where we're going to focus, and we're going to focus on the intersection between these two fields and how we use tools from this area to try to make understandings of this area. And so last time, we went through an example where you could see in action how we converted a big physics question, which was how do particles acquire mass, into a theory. And that theory was the so-called Higgs mechanism, where the universe starts off in a zero energy state, goes down to a lower energy state. When that happens, all the other particles acquire mass. And then at the experiment, what we look for is actually signals in our detector. And we saw that from theory, you could predict what type of signals you would expect to see in the detector. And so we predicted that we should see 4 leptons or 2 photons and a whole bunch of other signatures, but in particular, these ones. And then we went and took a look at the actual event displays from the detectors. And so we saw all sorts of pretty displays like this, where you have protons coming in. This is the ATLAS experiment, which you can identify from these toroidal magnets. You have collisions happening here, and then leaving energy deposits all over. And we stared at this a little bit. And then because I told you the answer, you could identify that what you were actually seeing here were 4 lines coming out, which were 4 muons, the heavier cousin of the electron. And this was a candidate for a Higgs boson decaying via 2 Z bosons to 4 muons. And then we saw how if we did this many, many times, so bunches and bunches of times, physics can actually come out of this. So once you identify all these particles and reconstruct what happens, you can end up with a plot like this, where this is the plot we saw last time, where it's the Higgs mass along the x-axis, which prior to these measurements, we had an unknown window where it could be anywhere kind of in here. You have the Z boson peak from the previous experiments, and then right here, this uptick in the data followed by the red curve predictions is the Higgs boson. And there you see that what we highlighted was that what we're talking about in the observation is really tens of events. So a very small number of events over billions and billions of collisions. And to me, this is really, really incredible. You're doing billions of collisions. Somehow you're identifying the particles either in real time or offline. You're saving the data and then ending up being able to make a statement about the universe with a very few number of them. And yeah.
I don't know if it's on that graph. If the graph doesn't exist, where would its energy level be?
Definitely not on this.
Not on that.
Yeah, definitely much, much to the left. Yeah. And so an important piece in all of this is that we need to make inferences about the particle properties. So like I just showed you one, which was a particle mass. We need to make inferences from measurements of all of these electrical channels. So in the current generation of experiments, we have millions of electrical channels. So this experiment right here, this is the CMS experiment. There's around 100 million electrical channels. The experiment I work on, the Atlas experiment, is a very similar number. And soon, after the upgrades, there will be billions of electrical channels. So billions of channels, billions of zeros and ones flying back to the computers. And we need to analyze all of this data and actually infer particle properties from it. And so how I want to go about discussing this is go through an important example, which is identifying third-generation quarks. Third generation meaning the top quark and the bottom quark. So these are the two most massive quarks that we know so far. And they can lead to event displays that look like this, where you have tracks moving through the detector in different directions. You have energy deposits deep in the innermost layers of the detector. And we want to make sense of this. Now, why I'm starting with this example and why this is what we're going to focus on today is that from understanding this example, you'll really gain a lot of intuition for the way that we think about the problems, the way that when we talk about detecting a particle, what type of logic we go through, different signatures in the detector, and because measuring these two particles has become a real workhorse of the LHC experiments and of the future experiments. So this will really give us a lot of insight. And to harp that even more of just how much we'll learn from doing this, this is the plot that we showed last time where it was the Higgs mass along the x-axis and then the probability of the Higgs to decay into different particles along the y-axis. And what we saw was at the mass point that we have, actually producing pairs of B quarks is the most likely scenario. And so by understanding how we actually identify these, you're going to be able to understand how we're gaining access to the most significant Higgs production mode, and you're going to be able to understand how we use these particles as a lens to new physics scenarios. So that was a rapid-fire refresher from last time and intro to the subject. So I'll just pause really quickly to ask if there's any questions or, yeah, I already see one.
I apologize if this was asked before,
No.
but is there any possibility of like fission happening, or did you put any safety protocols in place?
For fission? Okay. The question was, is there any possibility of fission happening? By fission, you mean breaking apart of the nuclei? Or you mean fusing together? Yeah, so we're constantly breaking these things open. Not fusion or fission in the way that you think of like a nuclear reactor exploding or something like that. That is not happening here, but it's happening here in the sense that we're taking nuclei and we're breaking them open completely. So similar but differences. Okay, so now to say again, what I'm hoping us to do is to walk through a qualitative example where we look at top quark pair production, and we get B quarks, and we're going to see how we go from a process, think about what signatures are left in the detector, understand different ways we can use those signatures in forms of algorithms, and then making inference with them. So the first thing I want to do was actually show you a familiar plot. So again, this is my favorite plot. This is, again, the interesting processes along this axis, the probability to make them along this axis. This is just for proton-proton collisions. And the process that we're talking about is this one right here. So producing a pair of the heaviest quarks. And it's, you see, compared to the rest of these, a relatively high probability process. This can be understood because we're shooting in protons where the charge of the protons that are shot in carry the color charge. And so you already have strong interactions. And so it's more likely that you produce particles that carry that charge. And for an order of magnitude scale, we're producing around 10 pairs of top quarks per second, or 100 million of them per year. So a really copious process. We have lots and lots of them, much more than when you start talking about probabilities all the way down here where you're getting, 0.01 per second, tens per year. So really, really copious. Would be great to understand more. And now what I want to do is actually walk you through what the decay or the production of particles look like. So what you're going to see on the next few slides is starting from left to right, we're going to see an evolution where you have two protons come in. I'm going to show you right here. I put a little diagram here which is showing two top quarks being produced. And they have a lifetime, a very small lifetime, of roughly 0.15 femtometers per C. Now, I know that this unit doesn't mean anything. It means very little to me, actually. And so I wanted to try to define a scale that we're talking about. So I tried to think of things that were big. And a thing that is big to me is the distance between us and the sun. And so if I define this as 1 meter instead of 149 billion meters, 1,000 times that is then roughly the scale that we're talking about. So if I go 1,000 times this, way over here, then the top quark decays right there. So to say it one more time, the scale that we're talking about is a femtometer per C. So this is to say if I move the speed of light, then it will travel roughly 1 femtometer. If I convert that into a scale that maybe feels more significant, that is like the top quark decaying here, and then 1,000 times this scale all the way over here is like 1 meter. So we're talking about extremely, extremely small scales here. Of course, so small that we cannot detect directly the top quark. So it decays, and now we need to ask, what does it decay into? Do we have any hope of actually studying this? So the first thing it decays into, well, actually kind of in unison, but the first thing I'll talk to you about is the top quark decaying via the weak force. So you get a W boson. The W boson is also very massive. It's around half of the mass of the top quark, and it also decays via a similar process. And so you get a lifetime that's, again, roughly femtometer scale. So again, it decays long, 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 long before you ever are even able to put a piece of metal there to actually do a detection. But then, when the W decays, you can actually get particles that may leave hits in your detector. So the W boson will often decay to a lepton and a neutrino. So that could be like an electron neutrino. More often, it will decay to a quark and an antiquark. So that could go to an up and a down, for example, up and then an anti-down. And these particles will not be the neutrino, so the neutrino will just move through the detector without interaction, so you won't see anything, so they'll be missing energy. The lepton can actually travel a non-negligible distance in the detector, interact with the material, and then the interacting with the material, you can actually get signals. And then the quarks can do a similar thing, but I'll mention it a bit more later. Yeah? of mass.
Like
Yeah, so this one, is the question that this one is massive, and then you drop to a low mass state here?
yes.
Yeah, so as this goes to a lower mass state, these then carry away energy. So it's a lower mass particle, but they have a lot of energy, so they're moving really fast.
All the energy moving really fast.
Yeah, because you have the conservation of energy and momentum together. And then when it decays, you get a lower mass state here, but a really energetic particle that shoots fast.
And many particles, or just how many?
From this decay here at W, you just get 2 at the initial. Now, these particles here, quarks and antiquarks, they can then shower a lot, but just 2 at the level we're talking about.
Just
2, yeah. And so now on the other side, what you have is you have the top quark, so it makes the W here, but then it also makes a bottom quark. And I write here bottom quark, but I really mean at the scales that we're talking about, a bottom hadron. And what this is saying is, remember from the strong interactions that we don't have quarks on their own. When they start moving, immediately they get bound inside of something, inside of a pair of quarks. And so what we get here is a bottom quark made, and then as it's still alive and hasn't decayed yet, it gets bound in another particle, and its lifetime is roughly a picosecond. And if you translate that into this particle moving at very high speeds, like what is produced here, it actually travels a few millimeters. So instead of it traveling the Earth versus 1,000 times the sun, it travels something that maybe at the detector scale, we can actually get a handle on this particle being produced here. But this isn't the end of the story. What you actually see is you see a production here, but then just like your question, you see a spray. So you see a lot of particles, and what's happening here is as the B quark's made, it's traveling, it's accelerating, it's radiating other particles like gluons. Then those gluons, as they lose energy, produce other particles, and you get a huge jet. And I'll show you an event display later where you can really see this jet of particles shooting outwards. And so the signature that you're looking for is a collimated spray. So you look for a collimated spray, and then you look for something weird on the inside. And so then if you take an alternative view, which is you go to the detector level, and for here, we'll just take a very simplified view of the detector, which is if I place the origin here, which is where the particles come in, then at roughly 50 millimeters, we have a tracker. Now this tracker, there's a magnetic field that is surrounding it. So as particles go through this material, they bend, and then they ionize the material, and you get measurements of electrons and anti-electrons moving. So you get an electric signal, and you get this from the range of 50 to 1,000 millimeters. This is a combination for our current detectors of silicon and tubes with gas inside of them. And so you get a measure of a momentum in here. And then in this region over here, you have materials where when particles go and hit them from roughly the range of 1 meter to 4 meters, they deposit their energy. So you get sprays of energy deposits in here. And so between these two, you get the momentum and you get the energy. So then you have a complete picture of particles passing through. And so like I said, in this region here, so if you have a spray of particles, they come. If they reach this material, then they can either keep going through, and then we'll have other detectors here. But for the ones we're talking about, they'll come through. They'll interact with the material here. What they'll really do is they'll hit a nucleus. When the nucleus gets hit, it'll get excited. When it gets de-excited, a ton of energy will be let out. And that energy creates an electrical pulse. We can then measure that electrical pulse. And so we see a mini explosion, basically. And we see mini explosions all over the detector, not literal explosions like with TNT, but electrical signals. And so we have a measure that you see this spray. But then I told you that inside of this spray of particles, you have a B quark or a B meson. And it travels a little bit and then decays here. And when it decays, it again produces a bunch of particles. And you can ask, if you take this particle here and trace it back, where does it go? So if I go back to here, all of these particles, you can trace back their origin to the interaction point. So you know, based on the magnetic field, that their original point is right over here. Whereas for a particle that travels a little bit and then decays, you can trace back its origin to a small displacement from the interaction point. And just to emphasize really how crazy this is at 50 millimeters, and I told you this thing is decaying few millimeters. So it decays after a few millimeters. You get a spray of particles. That spray of particles looks very similar to the other spray of particles, but you're able to trace back with millimeter precision that this decayed away from the point where the beams collided. And so between those, you end up with an event display that could look like this, like what we saw in the beginning. So this is the same one as before, and now you can maybe pick out what we're talking about. So you see these spray of particles here. This is one of those jets. There's maybe another jet here. There's maybe something over here. And then you have this long track here. And so you can look at this, and you have some measurements. I told you about two. The two I told you about were basically a huge amount of energy deposited on the outer regions from roughly 1 meter to 4 meters. And then I told you about some small displacement on the inside. So you have a collection of measurements. And then you have to make inference. And so before I go to this, I want to pause a second and ask if there's questions, because I'm sure that there is probably some level of confusion. Yeah.
So I'm catching this right.
Yeah.
Okay, your detectors are basically viewing really two things. There's the path itself, so there's a number of detectors
Yeah.
that can tell you the path,
Yeah.
and how fast it is.
Yeah.
But does the detectors also then detecting like the energy level, so the amount of voltage?
Yeah.
And those are really the two things that you have.
Yeah.
Okay.
Yeah. You really, I mean, what other things are there? There's, yeah, you measure the trajectory, you measure points in space, you measure the momentum, you measure the energy. From that, you have the energy and the momentum, and you can work your way backwards to the initial. Yeah, okay, there's a lot more details of how you actually run this, but yeah. Yeah.
It seems like you would need pretty high resolution in the sensor itself.
Yeah.
So they like triangulate where exactly the impact is?
Yeah.
Or
Yeah. So, for example, in this region here, we have silicon pixels. So we have really small pixels. We have currently, I think, 50 to 60 million. And in 5 years, we'll have 5 billion. Over from 50 millimeters up to, call it, 750 millimeters.
so is that like a tube?
Yeah, it's literally a tube. So you have the beam pipe goes like this. Then there's a tube around it. And that tube is lined with silicon sensors. Yeah, yeah. So I should maybe make that really clear one more time. How you should think about this is this right here along the x-axis is like you're going upwards, and then the beam pipe comes like this, and around it is our detector, so like a cylinder. And then that cylinder, like an onion, for example, there's different layers to it. And those different layers are the different components of the detector. And so then exactly like what you're saying, you have all of these electrical signals, and then you have to somehow triangulate and match the signals from here match signals from here. And so there's a bunch of algorithms running actually underneath the surface to even get to this. But I chose to brush over a lot of things. Yeah, let me go here and then there, and then I'll come to you.
Does that split the spin difference?
No, the question is, does this split the spin difference? No, this is from the charge. So you have a magnetic field, and positive charge will bend in one way, negative charge will bend in the other way. Not like the quantum experiments. No, not like the Stern-Gerlach. Yeah. Can you do a Stern-Gerlach experiment with this? Let me think about that. Yeah.
I was going to ask about detecting the spin, or is that an inference that is made based on theory?
An inference. It's an inference based on, well, for different particles, there's different things. You can look at the angular correlations between the particles you observe. So like, for example, a Higgs boson that is spin 0, the final state the particles you actually measure, the angular distance between them will be different than if it was, say, a spin 1 or spin half. So that's what you actually measure. And then you do an inference back. And somewhere in that inference back, you compare with simulations, and you, at this stage, trust that the simulations are right. And then, yeah.
This silicon,
Yeah.
is it pure silicon, no doping in it?
This one, there is doping in it. Yeah. The silicon in here, there's doping in it. There's silicon at different stages, and the next generations will have silicon, and there is doping.
There is doping?
Yeah.
So there's like a PN junction
Yeah.
or something like this?
Yeah, exactly.
Okay. So you generate a current?
Yeah. So the physical image is maybe you have something like this, like 2 levels. Particle goes through inside that gap. I mean, you know this much better than me. Electron hole pairs are made. The electrons drip up, the holes drift down. When that happens, you get electrical signal generated. So then you get a voltage. I saw your hand raised first, and then.
Do you need to detect the photons from the accelerating charges, or is that insufficient?
You do need to detect it. You don't have a choice of detecting it or not detecting it. Let me rephrase your question to make sure. The question was, as the particles are moving and accelerating, they're radiating photons, and those will go all over the detector. And do you need to detect them? The answer is you have to detect them. Those are actually part of the energy, and you have to add up all that energy to get a reliable measurement. And more than that, you don't have a choice. So long as the energy is enough that it excites the detector, you're going to measure it. Yeah.
So we are looking at the cross-section of one part of the LHC. So
Yeah.
So does the cylinder have all of these materials, or do these materials vary at different points in LHC?
Right. So the question was, we're looking at one point on the LHC, and we're talking about different materials. And do these materials vary at different points along the LHC? The first point is that on the LHC ring, maybe separate 2 things in your head. The LHC is the accelerator that's creating the particles. And then at 4 points, we collide them. And what we're talking about is one of those points. So there's 4 points. And here we're talking about, I'm trying to be general to include all 4 of them. Here we're really talking about the Atlas experiment. You can tell that because of where I put the magnetic fields. But we're talking about one, and then each of the 4 experiments, you'll get some configuration like this, different material choices, but so at 4 different points. Yeah. Any other burning questions? Okay, so you have something like this. Really, you have billions of things like this. And then you need to actually infer a particle property from this. And so you need an algorithm. And kind of the way I like to think about it when I was learning how to write these algorithms is I have some cartoon of my detector, creates a bunch of signals in it, and I need to design kind of like a magic 8-ball where I ask, is this a B quark? And then it says, well, as I see it, yes. As I see it, no. And so you're actually needing to design this tool here. And so you can think about different algorithms, which for us, an algorithm is you feed in some data, it does some operations on it, and then it makes a decision. And the first algorithm you could think of is a lot of people call me Tony, so the Tony algorithm, which is you just look at it by eye. So you just stare at this for long enough. You're a grad student, you just sit there and stare. And then you say, well, maybe there's something here. Maybe there's something here. I see some stuff here. You do some quick mental math in your head, and then you work your way backwards. And it's funny now, but this is the way that it was done for a long, long time. It was done like this because we were at much lower rates. So instead of having billions of collisions, we had tens, 20s. So you could really take pictures and look at them. And if you go to CERN, or even if you go to Fermilab, it's really fun to see where people take printouts from old detectors and put it up against like one of those, I don't even know what they're called, one of the machines where it projects onto the screen, the light, where you put it on, there's light shining underneath. And so, yeah, the old project, yeah, what I learned math on. And so you have this, and it actually projects, and you can go with a ruler and trace them. Yeah, exactly. So this now is kind of crazy. I don't think you can do this unless you really know a lot about the specific event. A different thing that you could do is you could make a rule-based game. So a discrete rule-based game where it's just like the game 20 questions. So you have a question, is it a B Cork? And you just walk down this tree of yeses and nos. And at each step, you ask a question. So the first question could be, do I see this so-called secondary vertex, the vertex where the B Cork decays and then it's the particles that originate from it trace back and don't go to the interaction point. So you ask that question, a yes or no. If you get to a no, then you say it's not a B Cork. If you get to a yes, you keep walking down. You say, is it collimated energy? So you keep walking down. This was a huge workhorse of the LHC and of the previous experiments for a very long time. It was extremely, extremely effective for kind of intuitive reasons, where a lot of our particles leave very distinctive signatures. So if we set up an experiment to produce top quarks, like, say, example, the Tevatron at Fermilab, you'll see a lot of the similar type of particles produced. And so you could put hard cuts and make this type of game. Now what's being done is we have a so-called continuous function-based decision. And all that is to say is we make some complicated equation where we feed in a bunch of the detector signals. So the signals coming from the energy measurements, the signals coming from the momentum measurements. We put it into a function. I write here f. It does some crazy operations on it. And then out of it comes the probability of a B Quark. So you can feel already, maybe just in how uncomfortable thinking about that feels, is that it's a level more sophisticated. Instead of just doing simple yes, no's at each step, you're saying I make some complicated function. Maybe there's a bunch of math in there, matrix multiplications, a bunch of stuff, and then out of it, I get a probability. And this is what's really being done, and it's being done using the ideas that we talked about last time, which are the same ideas that, for the reason that the Nobel Prize was awarded for inventing these so-called artificial neural networks. And so these are used all over the place now. And roughly the logic goes is you take the detector signals, you pipe them into the inputs, and extremely robust way, you can pipe in a bunch of different types of inputs. You can pipe in a discrete value, like it is a B Quark, it is not a B Quark, or you can pipe in continuous numbers. Let me say a few more things, and then I'll. And so you pipe them into the input. In here, which is the so-called hidden layers of the network, this is where the actual money happens. So a bunch of complex math operations in here. And then the output is a probability to either see a B Quark or, I wrote here, a C Quark, other types of particles. And so instead of having a discrete decision here, you have a continuous decision where you do an operation here. So an operation, an example of something like this, if you're doing facial recognition with your phone, when you look at it, it takes a picture of you, and then all of those pixels then come back, and it does operations on it to actually make the decision of if it's you or not. And very similar, we can pipe in all of our detector measurements and have similar operations running like that. Yeah.
Typically, how many inputs do you have? You have an awful lot of
Yeah.
information coming in.
Yeah.
It's coming in continuously, although you would take it stroboscopically.
Right.
And I'm just wondering how many inputs you have to get one output.
Right. So the question was, we're seeing probably a ton of data here. And how many inputs do we actually put in these things? Yeah, or how many wires are actually physically going? I think now probably an order of magnitude 10 to 100 features. That number is progressively increasing, and that's something that when we talk about future directions, I'll touch on a little bit more. But 10 to 100 numbers, something like that. For example, the algorithm that we use now for identifying B quarks, I think it's order 100, like roughly basically 100, something like that.
It takes how many microseconds to get a signal out?
The next question was, how long does the inference actually run? And that will be almost the entire subject of next lecture, because it's extremely fascinating. It depends on what computing you're actually running on. So if you run on a CPU, like what you have at home, it may take milliseconds. If you run on something more sophisticated, like a graphics processing unit, where they're doing a lot of the trainings, it may run in microseconds. If you're doing it on something even more advanced, like a chip that you build yourself, it may run in nanoseconds. And the different time scales here can operate at different parts of the experiment. So like, for example, the thing that I actually spent a lot of time on, and this week was in lab till 2 a.m. twice doing, is we build a custom chip, so a custom silicon chip, and on the chip, we write a neural network. So we actually etch into the silicon these operations, and we're able, from doing that, to make inferences like this at nanosecond scales. So really, really fast.
Generic instrument.
Yeah, yeah. So next time we'll talk a lot about that because it will become really important when we start talking about triggering and actually deciding what events you keep and throw away. How do you make decisions like this in real time? Yeah. So now what I want to show you was just what we gain from doing this. I tried to summarize it all, or find a plot that could summarize it all in a single slide, because I think that's a good way to look at these things. And so what you're staring at here is the year. So this is 2017. And this is roughly when a lot of the new computing hardware kicked off. So if you remember before, I talked about how the advancement of algorithms is going hand in hand with new computing technologies, and you're really needing these technologies to be able to train algorithms like this. And so around this time was when we really started to get hardware that we could do things on, like readily available graphics processing units. And so this is the year. The scale here is that 0 in some arbitrary units is the rule-based decision making. So where you just do yeses and nos. And then each of these are ever more sophisticated neural networks. The y-axis here is your ability to reject background. So the way that you can think about this y-axis is if you're wanting to identify Great Danes and your background is a bunch of cute chihuahuas, every time you see a chihuahua, what's the probability that you misidentify that it's a Great Dane? So the analogy here is these are your B quarks, these are your C quarks and other smaller mass particles, and you see a bunch of these, and then you ask, if I do 30 of them, if I see 30 chihuahuas, how many times do I misidentify it? And so you see a great increase here, where here, every 10 chihuahuas, we say it's a Great Dane. Over here, all the way from last year, it gets all the way up to the scale of, for C quarks, every 70 chihuahuas, and for all of the other particles effectively, all the way up to around 2,500. And to really emphasize just how incredible this is, if you remember the Higgs discovery plot, we're talking about tens of events. So if out of tens of events, you have a background where you have a huge background, your signal is only tens of events, and you misidentify your background very frequently, that tens of events will be just completely swamped in background. And so this gain here from a 1x over rule-based decision making all the way up to now a 5x is really, really significant and translates into extremely precise measurements. And the thing I wanted to emphasize in this is, cool, you have this new tool. But what's really exciting when you think about the lifespan of the LHC, which is maybe the next 10, 15 years, the detectors so next 3 years we'll install, 4 years we'll install new detectors, and then they'll be frozen. So then you won't change them at all. And so then what can you really do? You can change the algorithms that are running. And so what's really incredible here is basically with the same detector, you're just making smarter decisions by creating more sophisticated algorithms that run under the hood. And doing that, you're really able to identify all sorts of particles. So you can play a similar game where if you look at this picture here we already identified that this was a jet or a B quark. You can play a very similar game, identify that this here is an electron, this here is a muon, and then infer all the way down to the femtometer scale where deep, deep inside of here, even inside of the beams that are colliding, you produced a heavy top quark and it decayed. That is a great ringtone. Yeah, that's. I need to get that music after this. And so this technology is used really, really extensively. And I just want to highlight two examples of ones that I find really exciting. And so what you're seeing here is exactly what I told you we were going to see. So it's a Higgs boson that decays to its most frequent state, so 2 B quarks. And when it decays, there's also a Z boson going. And so you have Higgs to 2 B quarks and a Z boson going to 2 neutrinos. And now you can see that in here. So the Higgs is produced again, and it decays at the femtometer scale, so deep inside of here. Then it produces these 2 jets of particles. And now they're colored blue because we've identified that they're actually B quarks. So you can see 2 B quarks here, 2 B-initiated jets. And then it's recoiling against a Z boson, which is 2 neutrinos. And those neutrinos are represented, or the Z boson is represented as this dashed line because the neutrinos don't interact with the detector at all. So you don't see anything in the detector from this side. You see lots of activity from this side. And because now you can actually identify that these are B quarks and not some other random type of particle, you can now know that this right here is actually a process that really happens in real life and is exactly in agreement with the standard model. So this is being used all over for Higgs measurements. It's also finding its way into unexpected type of measurements. So this is a measurement that I work on currently and I'm hoping to be done with soon, where we shoot in 2 lead ions, so not protons, much bigger. When we shoot them in, the first thing you can observe in, maybe not in comparison to this, but in comparison to the previous event displays, is just how much stuff there is. The detector is all lit up. It looks like a Christmas tree. If you sat in the control room and you looked at the detector on the screen, every channel was firing. It looks like a mini bomb went off and poof, everything lit up. And somewhere in all of this, deep, deep, deep in the middle, right when the lead nuclei hit each other, 2 top quarks were made. And from those decays, you get an electron you get a muon, you get a B-jet, you get another B-jet, and you can actually understand that in all of this, you have 2 top quarks produced. Now, just on the surface, that may not be the most interesting thing. I mean, you say, okay, cool. I made 2 top quarks in a different collision system, so what? What's really exciting about a measurement like this is when you smash these 2 nuclei together, you basically melt the protons, and you gain access to deconfined quarks and gluons. So it's a type of plasma where the quarks are just kind of like a soup. And then you can ask, how do I actually probe it? Because the lifetime of it is, again, femtometer scale. Because the top quarks actually decay, their lifetime is shorter than when the plasma is made, you can measure the decay products of the top quark going through the plasma. And so it's very similar to like if you have you have a thing of water and you shoot a gun through it, you see a ripple that goes through. And you can really measure the ripple of these particles going through. And a lot of this is enabled by being able to identify things like B-jets, electrons, and muons. So the next years, a lot more of these measurements will happen. And so I'll pause for a second. I want to talk for maybe 10 minutes about future directions with this. But just pause for a second if there's any questions. Yeah.
How often can you do this before you degenerate the detector?
Yeah, so the question was, how often can you do this before you degenerate the detector or before the detector just breaks? I mean, it's electrical signals, you're bombarding it. Depends on the detector component. So the different layers of the detector have different lifespans. Yeah. So for example, the innermost layers where it's very close to the collision points, we already have electrical components dying. So after 10 years, we have, yeah. And so that's a big motivation, one of the big motivations for why we're doing upgrades right now. A different figure of merit, the innermost 2 layers of the detector will run once we install them for 3-4 years, but the rate of collisions will skyrocket because the LHC will be upgraded. So then after 4 years, we have to take out the innermost layers and replace them. So then it'll go down from 10 to 4.
You got to build that efficiency into your...
Yeah. So then the follow-up question to that was, well, if the detectors are dying, don't you need to bake that into the algorithm somehow, that actually the efficiency is going down? And I'm going to say that's exactly what I hoped that everybody's brain would start going. I gave you a very simplified version of this story. Anything that you can possibly think would happen does happen. Absolutely happens. You see it happening. You can see your algorithms getting worse as the time is going on. You have to update the algorithms, real-time calibration of them. All of it happens. Yeah. So it gets very complicated, Gabe. Yeah.
How do you even calibrate a machine like this?
Do I have enough time to? Yeah, I'm not sure I have enough time to say that. I can say a few things, which is, one, you need measurements of the detectors not when they're being bombarded. So before the LHC even turned on, before we lowered all of the electronics down into the shaft 100 meters underground, we set up beam experiments where you took the detectors and you put them like this and you shot protons at them. And so doing that, we knew exactly the energy of the incoming particles, and we could characterize the response. Now, you shouldn't love that answer entirely, because I'm telling you a perfectly functioning detector is sitting up above ground. I do measurements 15 years ago, and now I come all the way now and say they're okay. So then we do real-time calibrations where we actually ask for lower rates of collisions. So the LHC, we can tune how many collisions happen per second. And so we tune it so it's a lower rate, so we get more real-time measurements with less detector activity, and then we can actually do online calibrations. Now, between that 15 years ago and here, I could tell you maybe there's a million other things that happen, but all sorts of things like that. So calibration is a really challenging technique. Yeah?
Maybe I'm preempting what you're about to talk about.
Yeah.
But Google just talked about the fact that they've increased the efficiency, and I guess secondary to that
Yeah.
connected to
Yeah.
for me, please?
But yeah, so the question was, and I'm going to have a question back to you. The question was, I hear in the news someone like Google is increasing the efficiency of their chips, and is that helping you? Now, when you say efficiency, do you mean, I'll give you multiple things you could mean. Power efficiency? Error. I'll give you multiple things that could mean also. You can have you can have a simple error, like I have my electronics sitting here, I shoot in a 1, and then I just ask, did the electronics really see a 1? Maybe it didn't see a 1. Maybe it actually says it saw a 0. So that's one version of error. Another version of error is the algorithms running on them maybe getting better. That we're for sure doing. Another version of efficiency that you might talk about is power efficiency, which is probably a completely different thing than you were even thinking of, but is nonetheless extremely, extremely important. The electronics that we have operating need to operate at really cold temperatures. So the electronics on the innermost layers will operate ideally at something like minus 30 degrees Celsius. But you have constant things hitting it, so the temperature skyrockets. And more than that, if you just have, I mean, you know your computer at home, if you go on the internet and you watch too many YouTube videos, it gets hot, something like that. We need these to be extremely power efficient so that the physical chip really close to the detector doesn't get really hot. And so all sorts of these things are things we're optimizing. Yeah. I'll start right and then I'll go left. Yeah.
When you collide complete nuclei instead of individual protons,
Yeah.
does that create a hell of a lot more data to wait?
Oh, yeah. Oh, yeah. Well, maybe the answer is, oh, yeah, but then what we do. So it creates a lot more data in that the amount of detector signals is larger, but the rate of collisions goes down. So instead of every time two bunches cross, we have normally for proton collisions, we have maybe 60 protons hitting each other per time per bunch is crossing. For nuclei, we have on average, less than 1. So it's much rarer. So you have a compensating effect of the amount of detector activity goes up, but the rate goes down, and then you play that game. Yeah. Yeah.
Your answer on errors reminded me, I'm an FPGA designer.
Oh, boy.
And a few years ago, we started having to worry about errors just due to cosmic rays.
Yeah.
Oh my God.
Yeah.
You've got particles flying all over the place. How do you deal with that kind of, all the errors that are just happening just because of that?
Yeah. Yeah. Man, where can I start with this? So maybe I can start with the first thing, cosmic rays. I was actually also able to see this because I worked with FPGAs where you could see cosmic rays flying down and hitting them and the ones turning to zeros and going, what the hell is going on? Luckily for us, our experiment is 100 meters underground. So we have the Earth shielding us. Great. But the Earth is shielding us from the sky, but now we're doing mini explosions down there. So we're really careful with what electronics we put close to the interaction point and far away. So like, for example, FPGAs, we don't put right on the detector. We have cables going from the actual detector into a room that's maybe 100 meters away, shielded by a bunch of concrete. And in that room, we have all the computers, the FPGAs sitting there, and they run in there. But on the detector, we have electronics also, and then it's all not off the shelf. It's custom electronics, like custom chips, where they're made to be radiation tolerant. So we design something, we go and we test it in a proton beam. We just shoot particles at it for 5 years. We make sure that it's reliable, and then we install it. Yeah. 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 The comment was radiation hard chips. Yeah. It's if you go to Fermilab, they say it's classified, but I don't know who's using it right now. Yeah. Okay, so this is already leading us into future ideas. Kind of what I was hoping with that was to tell you just enough to get the big picture idea and then not tell you all of these details so your brain can start to wonder, well, what about this, and then inevitably reach a point where you go, oh my God, all of these things matter. And So now I want to tell you some future directions that we're heading. So one of the trends is a trend you already see a lot of in industry is so-called end-to-end predictions. And what this means is, basically in summary, you take the raw detector outputs, so instead of now 100 signals, millions, you train a neural network to actually read all of those signals, and you directly infer what happened on the femtometer scale. So you don't go through all the intermediate steps, you just directly predict from looking at the detector what's happening. And then I'm out of a job. Yeah. Now, I guess when I first heard this, I thought, well, this is really crazy. And then I spent 4 years doing a PhD where I did this. And what is interesting when you think about this problem is all of the steps that you're trying to get rid of when you do things like this. And so you start to think, well, if I'm actually getting rid of, say, identifying that this is a jet, and instead I'm just feeding it into a box, that's somehow undoing human work, which was actually by hand identifying these, which is probably something we should do because I was probably not that good at making those decisions anyways. So this is something that is early days of this, but will get more and more used as the hardware becomes available. The second thing is using these techniques to actually probe rare couplings. So everything that I talked about was measuring just the third generation, the heaviest quarks. These are the quarks with the strongest coupling to the Higgs boson. And so you could make a plot, which is the particle mass along one axis, and then roughly the coupling to the Higgs boson along the y-axis. And a very beautiful result is that they follow this basically linear path. An incredible, incredible measurement in theory prediction. And so far what we've talked about is the top quark, the bottom quark, the tau lepton, but you'll see no mention, except for the muon a little bit in here, of the second generation of particles, and especially not the first generation of particles. Why do you see that? Well, the coupling is smaller. They're even more rare. They're even more difficult to see in the detector. They're even more susceptible to all of these problems we're talking about, where if the detector starts dying, what happens? But maybe using some of these techniques, we'll actually be able to put onto this plot these other particle generations. And just to emphasize why that would be really, really incredible, we're interested in knowing why do we actually have different generations. The only difference between these generations is the particle mass. And that particle mass is entirely linked to its coupling to the Higgs boson. So measuring these couplings, i.e. putting them on this plot, is allowing us to check if there's any differences between besides the mass of these particles. And that would be a really huge measurement. The third thing is maybe you're looking for new types of physics, and it leaves unexpected crazy signatures in the detector. So this is an example of an event that I looked a lot at as a grad student. And this is not two nuclei colliding. This is two protons colliding. And you get tons and tons of jets. So you have jets all over the place. I mean, you can count like 12 or something. 1, 2, 3, 4, 5. They're just everywhere. This type of collision in normal standard model is extremely rare. Extremely, extremely, extremely rare. But in theories of new physics, you could get an abundance of collisions like this. Now, our current experiment is not really tuned. The algorithms running are not really tuned to actually measure things like this, and they're not really tuned to analyze events like this. And so new algorithms may help us do this. Yeah?
Doesn't the jet mean you got a number of jets, you got a sub disintegrate? You disintegrate into things that disintegrate.
Yeah.
And then you get jets
As a spray. Yeah. So
it tells you something about primary breakup versus.
yeah. So the question, let me maybe rephrase. Yeah, it's not really a question. It was more of a comment, I think, was that seeing all of these jets tells you something is happening. early on, because how you're getting these jets is from breakups of particles early on. And so when you have a lot of these jets, you know that there were many particle breakups initially, and that tells you something interesting.
You see that when you put in ions?
When you put in ions, you don't see something like this. Yeah. You see different types of things, but not a signature like this. Yeah. But point being from this slide is nothing actually to do with this in particular event display, just that you look at this and it's very atypical. And these type of atypical events is something that's common in new physics scenarios, and algorithms that we're designing can help with this. The last thing I wanted to say was actually to exactly your question, which was what we'll talk about next time, is the idea of triggering, which is that I said in the very beginning, we produce billions and billions and billions of collisions, but we don't actually have the bandwidth to save all of that data. And so we make decisions in real time what data to save. And we make these at the frequency that the LHC is colliding. So every 25 nanoseconds, we make decisions. And from those decisions, we only keep less than 0.01% of the data. The rest of it, gone. Completely gone. Not even saved on some tape that you put in a time box, gone. You never see it. And so these decisions that are being run in real time, extremely important. And the algorithms that were designed for that, they were designed in a way that were general purpose. We just turned on the LHC for the first time. We put in algorithms that could work for most things that we were interested in. But now as we start to do more and more measurements where we don't actually see any signs of new physics, the very ideas that created those algorithms you have to question. Because maybe our algorithms are just throwing away all of the events that you're interested in. Yeah, that would be a huge nightmare scenario, and something that people are taking really seriously right now. And so next time we'll talk more about this, and in that discussion we'll hear about different hardware. So we'll talk about FPGAs, for example, and different types of computing hardware that go into it. So yeah.
This is where the physics is really done.
Yeah.
Question there. Can you, if you did this directly in the great God of the machine,
Yeah.
give you a bunch of answers and yes to this, can you go back and see what the machine thought on the way?
Right.
What decision should you have made?
Right. Great. The exact questions. Okay. The question was, if we're making a decision in real time, and then we save some class of events, but we throw away a bunch of the other ones, can we then go ask the machine, why did you do that? And understand this? With the rule-based decision-making, where it's yes or no's, you can. You just go and you go yes, no. But then when you start to go to these more complicated algorithms where it's this huge mystery function, it gets significantly harder. How do you actually trace backwards? We don't have a good way to do that. We don't.
Quantum come into play?
Right, so the question would quantum, I assume you mean quantum computing, come into play here? Maybe I'll say two things. One, from our perspective, that would just be more computing power, so just be able to analyze more data simultaneously. It won't help with this problem of understanding what the box is doing. So for us, it's just more computing power, but my opinion, that won't happen on the lifespan of the LHC. I don't think we'll have a quantum computer. Me personally, maybe someone comes and corrects me, I don't think we'll have one on the scale of 20 years, 30 years. Yeah.
Because it can't keep the system.
No, because the machines, I mean, you can't actually keep them stable. so far, the quantum computing machines right now, there's too much noise, and you can do computations on them. Okay, I'm not an expert, so someone correct me. You can do computations on them for some amount of time, but they're nowhere near scale for a user to go and really use them. Yeah.
So the algorithms, you've touched on this a bit, the algorithms have already built into the logic of what you want to throw away. Is there some check about confirmation bias that is built into such a
Who's
system?
making that call?
Yeah.
You've sort of touched on that, but are there people sort of checking to see whether confirmation bias is happening?
Right. So the question was, these algorithms that we have running, you could even extend this to all the algorithms that we use in general. Are there checks for confirmation bias The answer is kind of yes. They're checked in that they're checked by us, and they're checked using simulations of what we think is happening. So they're checked in that sense. If you told me that the simulations were wrong, and actually there was new physics that we didn't simulate at all, and that modified what we would see in the detector, we would have no way to know. So we check with what we have, which is all these simulations from decades. But now as we start to probe new physics scenarios where you don't necessarily know what will be left in the detector, it's really hard to check. It's really, really hard to check. And so the algorithms, you play games where you try to make them as generic as possible. You don't want to make them too specific. Like if I made an algorithm that only targeted a Higgs boson decaying to 2B quarks, that would mean that I know for certain how that process happens. But from the simulation, you may not know this exactly. And so you can turn some knobs to make them more general. So we do that level. But if there was really some new physics scenario that we don't simulate at all, we would completely miss it. Yeah. Yeah.
These experiments of collision
Yeah.
were repeated over and over and over and over.
Yeah.
Is there a way of saying there is some repeatability of results?
Repeatability.
Is there, from one experiment to the next, to the next, to the next, is there something that is repeated? Okay.
Yeah.
To see definitely there is this type of collision is really producing this
Yeah.
type of result.
Yeah. So maybe if I somehow get all the way back, where would it be? This. This beautiful plot here is exactly like what you're talking about. The question was, effectively, each time you turn on the experiment, is there some way you reproduce results from the past? So you can have a reproducing experiment, i.e. doing science that is reproducible, that you can actually build on. And the answer is yes, absolutely. With maybe a caveat in that there is not another LHC. We don't have another LHC to turn on and redo the whole thing. But we have the colliders of the past that measured the properties of particles extremely precisely. So for example, like the collider that existed before the LHC produced a ton of Z bosons, and we knew its properties very, very well. And so then once we turned on the LHC, we measured all of those properties again really well and compared it to what we did in the past. So making exactly plots like this, where you compare the theory predictions, which bake in the experimental results of the past with what we're seeing now, is a confirmation of that. The other thing that we do, which was kind of designed into the experiment, is I keep talking about this ATLAS and CMS, these two big experiments. We have two general purpose experiments that sit at different points of the collider that more or less do the same type of physics. So we have copies of the two experiments, differences between them, but the only way that we believe any result coming out of the LHC is that both see it. So we've had instances where one collaboration has reported an excess, so seeing hints of new physics, and the other experiment didn't see it. And then you have to take more data, and keep cross-checking between the two. And this happens. So it's always fun. You go to conferences, and one experiment presents one thing. They say, we see new physics. And then the other experiment says, we don't see anything. And then you have discussions between them. So
This may lead to identify certain particles
yeah,
that are always produced,
yeah,
like electrons
yeah.
or particles. So in this case, can we infer that these particles really existed inside the mother particle?
So let me maybe repeat the question, because my brain maybe got a bit. The question was, from these experiments, can we infer that the particles are really real and not just a fiction that we're seeing, and that they come from the same parent? Was that?
The particles that collided
Yeah.
are the mother particle
Yeah.
that
Sure.
Okay, so in this case, we can say these children were inside.
No, not for this. So I think I understand what you're saying. You're asking, can we infer? We shoot in 2 protons, we see stuff come out. From the stuff coming out, can we infer that say the Higgs boson was actually inside of the proton? We don't infer that we don't go.
But the little ones, the electrons.
For this, we're not making comments like that. We're making comments about once you shoot in these 2, the protons basically disintegrate, and you just have a bundle of energy, and then you ask what come out. You could do other experiments, like, for example, the one that is being built right now in Brookhaven in Long Island, New York. What they're going to be doing is shooting in an electron beam and a nuclei beam. So if there's an electron here and a nuclei here, and the electron, when it comes, will effectively penetrate into the nuclei, and you can get a really nice 3D picture of what's happening inside the proton. So they'll be able to do things like that. At the LHC, that's not what we're doing. And actually, I'll talk about this a little bit more in probably the last lecture. They did do that at SLAC. Yeah, the question was, did they do that in SLAC? The last time they did it was at SLAC, and this is the next generation of it. Yeah. Okay, I think we're at 12, and I think Mary will probably. So thank you all for coming. I wanted to say Happy Halloween. And
And I used to work in Little City's lab, scanning nuclear emulsion, where we did this by eye.
Oh, yeah.
And this is automating that.
Yeah, to the nth level.
What bothers me about this is when you have, and another guy I know